Right, so this is the last lecture on the broad topic of duality in graph theory. And we have seen in the first two lectures duality between cut spaces and cycle spaces. Then we moved on to planar duality and saw what that has to do with the first type of duality. And today we'll start with a completely different topic, or so it seems, and then discover that it's very much the same thing or a similar thing, or at least closely related to the kinds of duality that we had before, both planar duality or plane duality and cycle space, cut space duality. So let's ask how many edge-disjoint spanning trees we can find in the graph. That's a packing problem. We want to pack edge-disjointly as many spanning trees in our connected graph as we can. Why is that a good thing to have? Well, suppose you have k edge-disjoint spanning trees. That gives you much the same thing as Menger's theorem gives you for k, that between any two vertices you can find k edge-disjoint paths. But you don't have to recompute these paths every time you're given two vertices. You can put your k edge-disjoint spanning trees in your database, and then whenever somebody comes and shows you two vertices that they want to be connected edge-disjointly by k paths, well, you just say, yeah, I can do that, and you look at your k trees, and in each tree you can find one path, and there's your k edge-disjoint paths between these two vertices. So Menger's theorem tells you when there exist, for any two vertices, k edge-disjoint paths. And now we want a stronger property that not only do they exist, but we can always find them in the same k trees that we have right from the start. So it's a stronger property than k edge connected. And when one gets that sort of thing, one question one can meaningfully ask right away is, well, can we get this stronger property, k edge-disjoint spanning trees, if we invest a little more in terms of the weaker invariant, namely edge connectivity? So is there a function f such that every f of k edge-connected graph contains k edge-disjoint spanning trees? Right? If we make the edge connectivity high enough, can we ensure that we get these trees high enough depending only on k, not on the graph that we consider? And the existence of such a function, f, is not immediately clear, I should think. Right? So for some huge 2 to the 2 to the 2 to the 2 to the k f value of k, if we have an f of k edge-connected graph, will that contain k edge-disjoint spanning trees? We'll answer that question in just a moment. So let me show you an obvious condition that ought to be satisfied in order for us to have k edge-disjoint spanning trees. And that is, take any partition of your vertex set. Say P is a partition of the vertex set V of our graph G. Any such partition, not necessarily interconnected sets for the start, then in order for us to have k edge-disjoint spanning trees, we ought to have enough cross edges that is, edges between partition classes, to join them all up in k-disjoint ways. Right, so how many cross edges, these are the cross edges for that partition, P. How many cross edges would we need? Well, we need at least the number of partition sets, order P, minus 1 for every tree, right? Every tree has to join up that many partition sets, and if we think of them as one blob, then the tree will induce something connected on that, the graph whose nodes are those blobs. In order for this to happen, we need its edges to be at least that many. Right? Now, if we want k-disjoint spanning trees, edge-disjoint spanning trees, then we need k times as many cross edges. So that's a trivial necessary condition for us to have what we want, namely k edge-disjoint spanning trees in our given graph G. And the theorem, the first theorem, and maybe the main theorem that we're going to have today is due independently to Tutte and Nash-Williams, both 1961, and the same issue of the same journal, Journal of the London Math Society. And they proved independently that this obviously necessary condition for the existence of k such trees is in fact also sufficient. So whenever it is true that for every partition of the vertex set we have that many cross edges, then there will exist k edge-disjoint spanning trees. So that's a nice kind of theorem, right? It's like Menger's theorem, like Hall's theorem, like various other theorems that we saw before in graph theory 1, whose beauty lies in the fact that an obviously necessary condition turns out to be in fact sufficient. And this beauty usually comes in various guises. So another way to express that is that we have some obvious inequality if we have here the number of edge-disjoint spanning trees in some given graph. And here we have the number of cross edges of some partition divided by order of that partition minus 1. So number of cross edges divided by this, we're aiming for k. Then we always have this inequality. These are always less than those. That's the trivial implication that I just showed you. Whenever you have a collection of edge-disjoint spanning trees, you're not going to have more than the k that you get for any partition up here when you divide the number of cross edges by the order of the partition minus 1. And the beauty of that aspect is that these two things meet. Right? There exists a value here that is both the maximum achievable here and the minimum achievable there at the same time. And when you have such a pair of solutions, so you have some collection, some largest possible collection of edge-disjoint spanning trees, say k, and you have some partition with the fewest number of cross edges, always counted divided by order of that partition minus 1. If you have two such solutions, then each is a certificate for the optimality of the other, right? If you have these trees, you can't have a partition with fewer cross edges, as we just saw. And if you have such a partition with so few cross edges, then you can't have more spanning trees than that. So they are certificates for the optimality of the other. And there's also a complexity theory way of expressing that, which I'm not going to go into. And there are some hints in the book about that. Okay, so it's like Menger's theorem, like other theorems that we have seen before, very pretty characterization. Okay, one observation, and that it is that it's enough for the substantial implication. The substantial implication is the backwards one, right? So that if every partition has enough cross edges, then we can in fact find these edge-disjoint spanning trees. And it's enough to assume this condition on the partitions for connected partition sets. So if we have a partition into sets that are not necessarily connected, then maybe what the partition sets induce or classes induce on G is disconnected. Then I claim, knowing that every partition into connected sets has enough cross edges, implies that this given white partition also has enough cross edges. And that's easy, because where are the cross edges of the white partition? Well, they're between vertices in different partition classes, and these vertices have to lie in some components. So they are cross edges also of the yellow partition, and conversely as well. Since these sets are components of what G induces on this white partition class, there are no yellow cross edges inside here. So all the cross edges that the yellow partition has are in fact cross edges of the white partition. Now, the yellow partition certainly doesn't have fewer partition classes than white. So if for every yellow partition, every partition into connected sets, we have enough cross edges, then this number is easily enough for white as well, because it's bigger than needed if it differs from it at all. Okay, so we can assume here in the backwards implication that the partition we consider have connected classes. Right, and now comes the answer to our question about this function f of k. How large is the exponential tower that makes that true? Well, the answer is it's not particularly large. 2k will do. I think that's extremely surprising if you haven't thought about it at all. And even if you have thought about it a little bit, I think that's wonderful. And why is that the case? Well, suppose you have a 2k edge-connected graph. Then every partition class, whenever you have a partition, must send out at least 2k edges, right? Otherwise, the graph wouldn't be 2k edge connected. You have a 2k edge connected graph. We want to prove there exist k edge-disjoint spanning trees, and we want to use that theorem. So it's enough to prove that every partition has enough cross edges. Well, every partition class sends out at least 2k cross edges. Now, we can consider the yellow partition or the white partition, it doesn't matter. When we now look at the graph that these cross edges induce on the partition classes as nodes of a contracted graph if they're yellow, or some other graph if they're white, then this graph on the partition classes has min degree at least 2k, right? Every partition class sends out at least 2k edges. A graph that has minimum degree at least 2k has epsilon at least k, right? Epsilon is the number of edges divided by the number of vertices. Okay, so it has at least k times number of vertices, edges. So how many cross edges are there? There are at least k times number of vertices of that graph on the partition classes, many cross edges, k times order p, which is bigger than k times order p minus 1. So we clearly satisfy what the Tutte and Nash-Williams theorem requires in order to give us our k edge-disjoint spanning trees. So that's a very surprising, I think, corollary, which maybe is the, I don't know, easier to remember. It's not the fundamentally more important, but the easier to remember version of that theorem. It's only a corollary, it doesn't go the other way. Okay, so now comes my publicity stunt for today. I'm going to give you a super short proof of Nash-Williams and Tutte theorem. And I challenge you to find the error. And whoever finds the error while I'm speaking will get a copy of the book. Okay? That's a safe bet. Nobody has ever done it. So don't feel bad if you don't. But I will honor that promise if you spot the error. The history of that short proof is rather more embarrassing than this stunt. The history is that I was sort of traveling into town on a day like this when I was about to lecture on this proof. And as I do for motivational reasons, I try to think of not just the proof I was going to tell the audience, but the obvious way of trying to prove that, and then to tell them why this doesn't work or something. So I thought of the obvious way, or one obvious way of proving that, and it worked, or so it seemed. So I walked into that lecture, and I didn't know why that proof wasn't correct. I didn't believe it could be correct because it was so short. I'm going to show you in a moment. But I didn't know where it failed. So I don't blame you if you don't earn yourself a copy of the book today, but you can try. Okay, so we need a weakening of the premise. The premise is that every partition has enough cross edges, right? And we're asking that only for non-trivial partitions. So we're making the premise weaker. That's fine, if we can still prove it. Okay, fine. What's a non-trivial partition? A partition is trivial if it has only one class, or if every class is a singleton, just has one element. Right? Those are trivial partitions, and we don't worry about those. We're just assuming that the non-trivial partitions have as many cross edges as the Nash-Williams and Tutte condition says. Okay, now we do induction. Or whatever you like. So, for example, the number of edges plus the number of vertices. We can always adjust that later when we make the graph smaller and want to say induction. We can see what we really need as the induction parameter. Take the number of edges plus the number of vertices. So we'll be getting smaller if we delete an edge or if we have fewer vertices. So I think we'll be safe there. Induction, start. Is K1. Okay, that looks a little worrying because K1 does satisfy the premise. The premise is that every non-trivial partition is made of blue cheese. It doesn't have any non-trivial partitions, so that is a little worrying because it always satisfies that. So it better satisfy the conclusion as well. Well, it does with a little adjustment. We want K edge-disjoint spanning trees of K1, right? So let's consider not sets of spanning trees, but families of spanning trees. This is not where the error lies. So if we allow families, we can take the same tree, namely the tree with the empty edge set, K times. Right, and that's disjoint from itself, edge disjoint. So that's true. So the induction does start. And now there are two cases. Case one, there exists a partition P such that, sorry, no, for every partition P, there are more cross edges than we need. So there are at least order P minus, order K times order P minus 1 plus 1 cross edges. One more than we need. For every partition, we have enough cross edges, but with one to spare. Okay, that's easy. Just delete any edge. Right, then we have a smaller graph. We have fewer edges. We can imply induction. Every partition of the edge-deleted graph with one edge less has enough cross edges, because these are the same vertex partitions as those, and there we had an edge too many. Now we still have enough cross edges. So we have K edge-disjoint spanning tree on the graph minus that edge. And we'll just take those. Okay, so the second, so when I say partition, I always mean non-trivial partitions in this proof, right? The second case is there exists a non-trivial partition with exactly K times order P minus 1 cross edges. Okay, so we're in that case now. Let's consider that partition. Let's consider a non-trivial partition class in it. It has at least two partition classes because it's a non-trivial partition. Let's consider one partition class that is not a singleton. Not all the partition classes are singletons because it's a non-trivial partition. So let's consider a partition class U that has at least two vertices. And now we ask, does the graph induced in G by this set U, does that have K edge-disjoint spanning trees? If it does, well, then consider the graph that arises from contracting U, or replacing all these vertices with one big vertex, and apply induction. All right? The contracted graph still satisfies the premise because its partitions induce partitions of this graph where U lies inside one partition class. So there are enough cross edges for the contracted graph because there are enough cross edges here. So we get, by induction, we get k edge-disjoint spanning trees on the contracted graph. G divided by U. So when I say contracted, just as a reminder, I don't require that U induces something connected in G. I just use the word contracted as well. Or we just work with connected partitions. Partitions into connected classes, as I said earlier, is possible. And then you can indeed contract. So that is not the problem. So if this graph has, this graph will have k edge-disjoint spanning trees by induction. And it will contain this one node that corresponds to U. And these spanning trees all get into U at some point. And now in U, for each of these k spanning trees, we take the G-induced U. Right? We said we're in the case where there are also k-disjoint spanning trees here. So the third spanning tree of this graph now gets blown up into a spanning tree of G by inserting at the node big U of that spanning tree, the third spanning tree from this. Right? So the spanning trees, the third spanning tree here has edges coming into this big blob, this big vertex U. And these edges are really edges of G, landing in some vertices here. And at these vertices, we can connect them to the third spanning tree of this. Yes?
How is it guaranteed that U will always be one subtree and not different parts of U connected from different other components?
Well, we're working edge disjointly on the various trees. So the first tree here gets blown up by the first tree here. The second tree here gets blown up by the second tree here. So what we do with each tree has nothing to do with what we did with the other trees. Does that answer it, or did you mean something else?
So we assumed already that U has k-disjoint.
Yes, that's a case we're in. That's an assumption that we have k edge-disjoint spanning trees on this. That needn't be true. We'll deal with whatever happens when it isn't true. Okay? Yeah?
Could it happen that we get a cycle
No, that can't happen because such a spanning tree in this graph has this big node U somewhere, and then these edges here, they're edges of the contracted graph of this graph, and they're really G edges that go to some vertex of G inside this set U. Right? And in this set, they land on the yellow spanning tree that we have in here. There's not going to be a cycle, no. Or you can use the other criterion for trees. From every vertex, you can get uniquely to every other vertex. Maybe that's easier here. Right. No, I'm sorry, the error wasn't here. So that's done. This case is done. Let's now assume that we don't have k edge-disjoint spanning trees in here. Okay. Now we apply induction to this graph. This graph is smaller. What G induces on U is smaller than the whole thing because the partition was non-trivial. There is at least one other class. And partition classes by definition are non-empty. So this is indeed a smaller graph. We can apply induction to that. And then since there are not k-disjoint spanning trees, we know that this has a partition with not enough cross edges. So U has a partition and there are not enough cross edges of that partition to give G of U k edge-disjoint spanning trees. So not enough cross edges there. So this partition, call it Q. Of this graph, and it has fewer than k order Q minus 1 cross edges. Right, but now consider, well, you know what's coming, right? Now we consider the partition of G that is obtained from the given partition P by refining this class U by Q. And you can work out that this partition doesn't have enough cross edges. I'm not going to write the inequality up here, it's easy. I have it on here for you. How many cross edges does this refined partition P prime have? Well, it has fewer than k times order Q minus 1 cross edges in here. And it has exactly the right number of cross edges between white, because that's the case we're in. Right? And because we're tight on white and below par on orange, we're also below par on the combined partition, the refined partition P prime. If you just add these two things together, then you get this k is a common factor here. So you get the number of partition classes P prime is, what is it? It's number of partition classes in Q plus the number of partition classes in P minus 1 for U, because U is no longer a partition class in P prime. But never mind, so we get this equality here, and that turns out to be exactly k times order P prime minus 1. We have fewer than that many partition classes. End of proof. I'm not going to linger on this because we have a lot to do today. It is an exercise, and of course, I mean, you must be able to, really, you must be able to go through the proof and check each step where it fails. If you can't do that, then you shouldn't be sitting here. So you should have learned that in year 1. But it's damn hard. It is hard. But you really, really have to be careful. So it's a lovely exercise in being precise, and a lovely exercise in checking whether you've just persuaded yourself of something that isn't true, which very much applies to your own work as well, where it's even harder because you're so, you have so much in the back of your head that you tend to think when you're checking your own proofs rather than what you wrote down, that it's even easier to miss errors that you made. So as an easy exercise, find the error in this one. Don't just find a counterexample. It's much easier to find a counterexample. Please don't try, not at the start. If you really can't find the error in the proof, find a counterexample and then see where this counterexample fails in the proof. And obviously you'll find it. Okay, so it's a lot of fun. Okay, so now a completely different question. We talked about packing spanning trees into a graph. We wanted many spanning trees in a given graph, edge-disjoint spanning trees. And now we're asking something different that will turn out to be something like a dual question, and that is with how few spanning trees can recover all the edges of a given graph. Now, these don't have to be edge-disjoint, but we want as few as possible. And we don't even ask that these should be spanning trees in the graph. We can, but we don't have to. Just trees on the vertex set. We are looking for as few as possible cleverly chosen trees on the vertex set that between them cover all the edges of G. And how few can we get away with? Okay, so here again is an obvious necessary condition. Let's look at a subset of the vertex set. Call it U again. And if we can cover the entire edge set of G with only k trees, then on this particular set of vertices, and indeed on any other set of vertices, there must not be too many edges to cover. So how many edges can you cover with k trees? Well, k times each tree can cover how many edges? Well, order of U, number of vertices in U, minus 1. Right, so in order for us to have k trees on V that cover the edges of G, it must be true that for every vertex set U, there are no more than this many edges of G on that set. That's a clearly necessary condition for the existence of a covering by at most k trees of our graph G, and this theorem of Nash-Williams a few years later, 1964, says once more that this obviously necessary condition is in fact sufficient. So if for every set U there are not too many edges on U, no more than that, then you can in fact find k trees that cover the edge set of G. It has all the same bells and whistles as Menger's theorem and as the tree packing theorem. You can rewrite it as an obvious inequality that you can satisfy with equality. You can write it as certificates of two optimization problems to cover or many edges on a given set that certify each other's optimality and so on. And I won't do that again, but you can do it for fun. It's, again, that sort of theorem. And the smallest number, the smallest k, it's possible to have k trees covering the edges of G, is called the arboricity of G, right? And the arboricity, this arbor, which means tree, comes from this. So once more, the arboricity of a graph G is the smallest k such that of the edges of G can be covered by k trees, only k trees, on its vertex set. Now, by the theorem, this is also the maximum number of edges on any subset of the vertices divided by this. So once more, the arboricity of G, this minimum number of edges in a covering by trees, also is the maximum number of edges that any set of vertices can have divided by that number minus 1. So it's something like the local density of G. And that makes the arboricity an important invariant. It's not so much these trees, but it's that the arboricity of G is the greatest possibly local edge density, not in the sense of extreme graph theory, but in this sense here, that you can have. Okay. Now, that's called the covering problem. And, let me show you that the covering problem and the packing problem are very much related. And I'll show you that by rephrasing them in as unnatural ways as I can. And the benefit of that is that the most unnatural way for each of them will then look very much dual to each other. Okay, so the packing problem. What does that ask? It wants us to maximize K such that there exists at least K edge-disjoint spanning trees in the graph. So let's make that our first way of phrasing this. So edge-disjoint spanning trees in our connected, always connected graph G. Okay. Equivalently, we could ask that we partition the entire edge set of G. These spanning trees don't have to use all the edges, but if we want to use all the edges, we can. So we want to maximize this case so that there exists a K partition. Okay, so that should go in here. There exists a K partition into K sets of the edge set of G into sets F, sets of edges, such that the graphs they induce on the entire vertex set are all connected. Right? The trees do that, and we throw in the remaining edges of G to get a partition rather than just subsets. Okay, so that's clearly equivalent. If we have such a partition here, then in each of these connected graphs we can pick a spanning tree and we get the first condition. Okay, and here comes the weird way of rephrasing that. We might throw in the other potential edges as well. So we might ask for a K partition of the set of all potential edges on V, the set of all pairs of vertices. And what should that now satisfy? Well, it should such that every class meets every cut, or equivalently every bond of G. Okay, so if we have such a partition of the edge set of G, we just enlarge it, extend it to a partition of all the potential edges. The edges that are not in G don't bother us, because in this condition here, we're asking precisely what we asked there, that each of these partition classes is connected just on the strength of its edges that lie in G. Here, it meets every bond of G for every partition, bipartition of the vertex set. It must have an edge across, an edge of G across. Okay, and then the theorem tells us that there's a characterization. The characterizing condition ensures that every contraction minor of G, whenever we contract Will-log connected partition classes, has enough edges. Okay. That's the packing problem. And now let's look at the covering problem. And there we want to minimize K such that there exists, well, the first one was K spanning trees or trees on V that between them cover the edges of G. Well, if we have such trees, they may cover some edges of G more than once. Okay, we can delete those without losing covering from all but one of them. So this is the same as asking for K forests on V that cover the edges of E between them. And now comes the weird way of rephrasing that. And that is that there are there's a K partition of all the potential edges on this vertex head V into classes. Let's call them F, such that for each of these classes, the complement, the other edges, meets every cycle of G. Right? The complement meets every cycle of G is the same as saying that the set itself doesn't contain a circuit as an edge set of a cycle, and that is acyclicity that defines forests. Okay? So now the characterization, the characterizing condition in the theorem we've just seen ensures that no deletion minor of G, a minor you obtain by deleting edges and possibly vertices, has too many edges. So the deletion minors I have in mind are those subgraphs induced on a vertex set U, and none of them must have too many edges. That's what this characterization tells us, with the appropriate values of too many and enough. Right? And you see how these play out against each other. They're very much dual to each other. We have partitions of the entire set of all possible edges. And here we say that every class, partition class, has to meet every bond. And here we say that the complement of every partition class has to meet every cycle, every circuit. Right, so it's the bonds and the circuits that are coming into play again. And so, yeah, I wanted to show you this just to alert you to some mysterious or not so mysterious connections to what we've done before. And this kind of duality comes from or is formalized in matroid theory. Graphs are special cases of matroids. Vector spaces are also special cases of matroids. And matroids are set up in such a way that they have duals. Graphs don't always have duals. Planar graphs have duals. But all graphs viewed as matroids have matroid duals. In matroid theory, this duality is enacted in a very clean way. And the theorem that I want to show you solves both the packing and the covering problem once. And the theorem, the natural home for this theorem is indeed matroid theory. But I'm not going to what matroids are here. But here's the theorem. And the theorem says that for every graph, not every graph that has, I don't know, enough edges or not too many edges or something like that, but for every graph you can get an aspect of both these things at once. And there it is. For every connected multigraph, so graphs are now multigraphs because we want to preserve all the edges, like cross edges in a partition, even when they become parallel edges of a contracted graph. So for every connected multigraph, there exists one partition. Here's our graph G, and there exists a partition P that satisfies two things at the same time. One is that, on each partition class, you get k edge-disjoint spanning trees. On each of the partition classes, you get k trees, just on that class. And between the partition classes, you get a covering. By trees on that contracted set of nodes. Okay, so we can get both at the same time. We're going to prove that today. Before we do that, I want to show you how easy it is to derive both these theorems that we had earlier from this one theorem. Okay, just one remark. I said that the graph we start with should be connected. That's not technically necessary, but makes our life a little easier. Okay, so even disconnected graphs have such a partition where these partition classes do contain k trees. So obviously, in particular, those partition classes will be connected. And between partition classes, you will have a covering by k trees that don't need to have their edges amongst those edges of G, as we said earlier as well. Okay, so let's deduce the packing theorem from this packing covering theorem, the central theorem. Incidentally, not only is this theorem true for matroids, but for infinite matroids, it's the overarching, most important, most fundamental problem, open problem. So there is an infinite version of it that is unknown whether it's true or not, and that implies all sorts of other open problems in infinite matroid theory. So that is a really nice way of focusing on exactly that big problem by packing covering. Right, so back to finite graphs. We want to deduce the packing theorem from this statement of the packing covering theorem up there. So we're for the non-trivial direction, we're assuming that every partition has enough partition classes, and we want to get at least k trees. Okay. And we're using the fact, this assumption that every partition has enough cross edges only for this one partition P that we have in the theorem. This one partition here has enough cross edges. Okay, and if it has enough cross edges, well, then you can do the same thing as we did earlier in the false proof. These classes have k trees by assumption. That's how the classes are defined. It's a property of those classes. Then between them, there are enough cross edges. So we need to show that this contracted graph has a covering, has a tree packing by k-trees. And then they can be expanded by the corresponding k-trees from each of these classes to give our desired k-trees for the entire graph. Now, why should it be true, given the packing covering theorem, that there are k spanning trees in the contracted graph G minus G contraction P, this one? Well, the theorem says that this contracted graph has a covering by k-trees, right? The covering by k-trees is not necessarily edge-disjoint. Yeah, the partition P was chosen, or the covering packing theorem asserts that there exists a partition P, such that in particular the factor graph G divided by P has a covering by K trees. So these are not necessarily disjoint by definition, but they are in fact disjoint. And why are they in fact disjoint? Because being a covering, they cover the cross edges of this partition, and by assumption in the packing theorem, of which we're trying to prove the non-trivial direction, in that assumption, there are many cross edges. There are k times order p minus 1 cross edges. So if we can cover all those by k trees, well, these trees had better be disjoint, otherwise they can't cover them. So these trees are not only, they don't only cover the cross edges, but they are in fact a packing of G contracted P, simply because otherwise they couldn't cover. Okay, so that's one. Now let's deduce the covering theorem from the covering packing theorem. The covering theorem says that if for every vertex head U in G we don't have too many edges on U, then we have a covering by at most k trees on the vertex set V, covering of all the edges of G. We know that there are, from the definition of the partition, that there are k edge-disjoint spanning trees on each of these partition classes. Now, they don't necessarily cover all the edges in such a partition class. They just sit in there edge-disjointly. So by definition, they don't cover all the edges, but in fact they do. They cover the edge sets on U because there are not so many edges, right? If they're edge disjoint, which they are by definition, they cannot afford to not cover the edges of G of U. Okay, so then we can do the same thing as before. We combine the trees from these classes G of U with the trees that we get on the contracted graph GP, and together they make a covering of all the edges of E. So it's really, really easy to get both these theorems from the packing covering theorem. Okay, so let's prove the packing covering theorem. And in order to prove it, we need a few more definitions, just a couple of definitions really. And one is if we have a spanning tree, or if we have, and look at a chord, E, then we can modify that tree by deleting an edge from its fundamental circuit and adding E. Then we get another tree, right? So if this is a spanning tree, E is a chord. If we delete E and add, if we delete the edge F from the fundamental cycle of that chord E, delete F and add E instead, then we still get a tree, right? We're still connected if any path wants to use F, and F is no longer there, well, it can get from here to there via E that we have added. So we haven't lost connectivity, we have the same number of edges, so we still have a spanning tree. That's called exchanging F for E. And an exchanged chain, E0 to En, is called an exchanged chain of edges. With respect to some set or family, it'll be a family later, of spanning trees, call that family curly T, if each of those edges can be exchanged for the edge after it, exchanged for the next edge, I plus 1, with respect to some tree in our family, right? We can add E0, we can find a tree that contains E0 and doesn't contain E1. We can find a tree that contains E1 and doesn't contain E2, and so on. So we can exchange them. And that's the important condition. En, the last edge, does not lie in any of the trees in our family. Okay, and here's a little lemma, and that says, the lemma says that if we have such an exchange chain, and E0 happens to lie in 2 trees here in this family, then we can modify the family of trees to get another family of trees that cover more edges. And the idea is, well, the obvious one. Lemma 245. E0 exchanged for E1 and E1, and that changes some tree in our family curly F. Yeah, I won't give you indices on the board here. The indices are in the formal proof. Right, this modification here, deleting E0 from some tree and adding E1 changes that one tree. And the idea is to keep doing that. All the way up to En. Now, E0 started out lying in two trees, right? Then we deleted it from some tree, but it doesn't matter because since it was in two trees, all the edges of the family afterwards will still cover this edge E0. And then the other edges, E1, E2, E3, and so on, were deleted from some tree. EI gets deleted for EI plus 1, but only after it was added when EI minus 1 was deleted. So we add E1, but E1 gets thrown out in the next step, in the second step, and replaced by E2. E2 gets thrown out in the third step and replaced by E3, and so on. So the set of edges covered here is not going to change very much. In fact, it's not going to change until the very last step where En is added. And that's fine. So that's exactly what we want. Now, is there a problem with that, or was that the proof? Well, there is a problem because the assumption in the definition of exchange chain just says that there exists a tree in the original family where a given edge can be exchanged for the later edge. But we modified those trees. Right, so the first tree was modified by deleting E0 and adding E1. It could happen that the same tree might be needed later for an exchange EI to EI plus 1. And that may no longer be possible. It may no longer be possible, for example, because EI plus 1 is no longer a chord of that tree, or EI is no longer on that tree because it was deleted earlier. So that is a problem, and the formal proof is nearly a page long because it keeps track of all the indices and families of trees used at different steps and so on. But informally, the idea is really easy. And the answer is, yes, these trees can change, but not in a way that makes the exchanges that are planned impossible if this exchange chain was chosen minimal. By minimal, I just mean with respect to cutting out some elements, preserving the property that this whole thing is an exchange chain, with respect to the same curly T. So that was a bit short, perhaps, but that's how the lemma is proved, and now the main proof of the theorem works as follows. We have to find this magic partition P in the packing covering theorem. And the way we do that is we just blindly take a family of spanning trees that between them cover as many edges as we can. And how do we get our partition P from this family curly T of trees covering as many edges as we can, well, we look at the set of all edges that start an exchange chain with respect to this curly T. Okay? So in particular, all the edges that are not on any of the spanning trees, they start the trivial exchange chain. And then we partition V into the components of the graph defined by these edges in D. Just the edges that start an exchange chain. And that is going to be our partition that we want in the theorem. Now I have to prove that this is, in fact, a partition that does what we want, right? So these edges here all start an exchange chain with respect to this fixed family of trees, curly T. Okay, so what are we asking? We're asking that on each partition set, U, there exists K disjoint spanning tree. Let me draw this a little bigger so like we can play more with it. So this is our partition set U. And we need K edge-disjoint spanning trees in there. Now what we can define straight away is this subgraph of what a spanning tree Tj from our family induces on U by the edges that this spanning tree has in D. So once more, we have these K spanning trees, T1 to Tk. Their edges are not necessarily in D, but some of their edges are. So if we look at Tj, the jth of our K trees, and then look at its edges in D. Some of them are, others are not. Then these edges in D define a subgraph on U, which has maybe more than one component. I'm going to show you that it's only one component. But the subgraph I call Sj, and I want to prove that Sj is connected. These Sj are edge disjoint for different j's. If we had an edge of D lying in two Sj's, S5 and S6, for example, then this edge would be an edge E0 that lies in two trees, T5 and T6, and then that can't happen by the lemma, right? The lemma said if E0, if some edge E0 lies in two trees, then there is a family of trees that cover more edges. But KDT was a family of trees that cover as many edges as we can cover by spanning trees. So this doesn't happen. Okay, let me just delete it. These SJs are disjoint for different Js. So let me show they're connected. If we had two vertices in U in different components of Sj, well, we can link them up in Tj. So there is a path in Tj, and let's consider that path. From this one vertex U to the other vertex U prime. Here is the path in Tj from one vertex to the other. But now, we can consider the edge E from U to U prime. And I want to show you, in order to prove that Sj is connected, I want to prove to you that this entire path in Tj from U to U prime does not, in fact, leave U, but lies inside this vertex head U, right? If I can prove that, then from any vertex in this head U, you can get to any other vertex on Tj without leaving U, and that is exactly what we want, that Sj is in fact connected. Consider any edge on this path from U to U prime outside U. It could be this edge, doesn't matter, any of those. And now I'm going to show you that this edge lies in D. Right? And that is going to be true for all these edges here, because I just consider each one of them. And if they're all in D, well, then this path is a path that, in fact, lies in D. But then it shouldn't have left this component at all, because that's how these partition sets were defined. They were the components that the edge is in D induce on V. So any path that lies in D stays within its one component, so it doesn't leave, in this case, U. Okay, so we need to show that E prime, every E prime on this path lies in D. But how is D defined? D is the set of all edges that start an exchange chain. This edge here is an edge in D. And why is it in D? Because it starts an exchange chain. E, E1, En is an exchange chain. But now we can precede that exchange chain by E prime. And that's another exchange chain, because there exists this tree, Tj, where we can exchange E prime for E. So we have shown that E prime is in fact in D, and that's what we needed to show in order to show that Sj is connected. Now we contract in each Tj these partition classes U, which we now know are connected in that tree, in each of the trees. And then these trees, T1 to Tk, define on the contracted graph spanning trees T1 prime to K prime. Now, the edges that are not edges of any tree in curly T, that are not covered by curly T, they, as I remarked earlier, form trivial exchange chains, so they lie in D. We contracted the edges of D, so the edges that remain in the contracted graph are precisely those in the minor G divided by P. But the Tj prime, they cover these edges that remain here in the contracted graph. And that is exactly what we needed to show for the theorem.